So this lecture is the start of kind of a long journey. What we really want to do is define something called a logarithmic function, right? And there's several steps we have to go through to get there. Logarithmic functions are defined in terms of exponential functions. So first we have to talk about exponential functions. And specifically, they're defined as the inverse of an exponential function. So before we can do that, we have to talk about inverses. And inverses are defined in terms of the composition of two functions. So again, before we can talk about inverses, we have to talk about function composition. And that's what we're going to start here in this lecture. So to motivate this, I've got a couple formulas here. And what I want to do is I want to calculate the momentum of a 1 kilogram object after it's been dropped from a certain height, let's say h meters. And the problem is there really isn't a physics formula to do that. All right, now what there is there's a formula that we can use to calculate the velocity of an object that's been dropped from a certain height. And then there's another formula that I can use to calculate the momentum, right? That's what we're looking for, of an object based on its velocity. Right, so you see this is kind of turning into a two-step process. Right, so let me simplify my formulas a little bit here. Right, we're talking about, let's see, a 1 kilogram object. So I know the mass, right? That's the m in my momentum formula. So m is going to be 1. So this momentum formula simplifies to just 1/2 v squared, right? And this g over here in the velocity formula, that's a constant. It's the rate of acceleration due to gravity, which is 9.8 meters per second. So this formula simplifies to the square root of 2 times 9.8. That's 19.6, and we still have the h. All right, so what I'm going to do here is I've got this little table, and I'm just going to work out some numeric examples just so you can kind of see what this process is looking like. Right, so first, let's say we're dropping this object from a height of 1 meter, and I want to know what its momentum is. Right, well, my velocity formula says that the velocity is the square root of 19.6 times 1, which my calculator says is 4.43. And then I can take that number and I can put it into my momentum formula, right? And I get that the momentum is 1/2 4.43 squared, which is 9.81. Okay. So let's try one more here, right? Just to kind of see the process again. And I kind of got scrunched up there with space. So let's jump down and do 3. Right? V of 3 is the square root of 19.6 times 3, which my calculator says is 7.67. And so then to get the momentum, I'm going to take this number, put it into the momentum formula. I'm going to get 1/2 7.67 squared, which is 29.41. Okay, so now hopefully you're starting to see the process, right? First, I take the height number and I put that into the velocity formula, and I get an output. And then I take that number and put it into the momentum formula. So in a sense, the output of one formula becomes the input of the next formula. All right, so let's look at the next slide here. And I've worked out a bunch of these values, right? I just kind of filled the table in for heights from 1 up to 5. And yeah, okay, I mean, this is working and all, but it's a two-step process. And I always think like a software developer, because that's what my background, my professional background is. And I'm always thinking I want to minimize the number of steps. So the fewer steps, the faster the program, and the fewer steps, the less likelihood there's going to be an error, right? So here's what I'm going to do, right? I mean, I've been doing this with numbers, right? 1 goes into the first formula, a number comes out, that number goes into the second formula, and the final number comes out. Well, you know, what if instead of doing this with numbers, I did it with the formulas? Okay, so instead what I'm going to do here is I'm going to put h here. And if I put h into the velocity formula, I get the square root of 19.6 h. And then I'm going to take this result and I'm going to put it into the momentum formula. This is 1/2 the square root of 19.6 h squared, which is 1/2 times 19.6 h, which is 9.8 h. Right, and now look at what I did. I have a formula for the momentum that is purely in terms of h. This is what we're talking about when we talk about function composition. Right? I'm taking one function and putting it into another one and getting a new function as a result. So here's how we write this, right? This kind of big open circle here means composition. So this is the composition of G with X. And this is equal to this expression here, right? And you notice this is exactly what we did on the previous slide, right? F was that rho. So I didn't mention that. That's the Greek letter rho, right? It kind of looks like a P. It's the symbol the physics guys use for momentum. And my G function was the function for the velocity. You need to know this notation on the left. Anytime I'm doing a problem, right, and I see function composition with this open circle thing, I almost always immediately replace it with this. Because that tells me exactly what I'm supposed to do. I'm supposed to take the G function, put it into the F function, simplify the result, and what's left is the composition of the two. All right, so that's kind of the basic idea of composition, right? It's what we're trying to achieve, and we've got some new notation. In the next lecture, we're going to look at some examples and see how this actually works in practice.